We have all felt that uncomfortable, burning, churning in our stomachs after eating a little too much. When that happens, you might reach for a spoonful of baking soda dissolved in water to settle things down. That simple home remedy is a perfect example of how the liquids in our world are divided into two opposing teams. On one side, we have the acids, which you know from the sharp, sour taste of lemon juice. On the other side are the bases, which taste bitter and feel slippery to the touch, like soap. Since we cannot safely taste every liquid to find out which side it belongs to, we use chemical indicators. These are substances that change color to reveal a liquid's team. Drop an acid on litmus dye, and it turns a strip of litmus paper red. Drop a base onto a turmeric curry stain, and that bright yellow turns deep reddish-brown. Every time you scrub a stain, bake a cake, or digest a meal, you are watching a localized match in a massive, invisible chemical sport playing out right in front of you. This chemical divide operates on a massive scale. Look at Venus. The thick, yellowish cloud cover wrapping the entire planet is made of concentrated sulfuric acid, making the atmosphere incredibly hostile to life. To understand how these sides compete, we have to look closely at their microscopic players, known as ions. You can think of an ion as a tiny charged particle, but acids and bases need an arena to play in. When an acidic compound dissolves in water, it releases positive hydrogen particles. We call these H+. The opposing team brings a different tool to the field. When a base dissolves in water, it releases negative hydroxide particles. We call these OH-. On their own, as dry powders or gases, these chemicals often sit quietly. It is the addition of water that pulls their molecules apart and activates these hidden abilities. This diagram shows the pH scale, which is the tool we use to measure exactly how many of those positive hydrogen particles are in a liquid. The scale runs from 0 to 14. Pure water sits right in the middle at a perfectly neutral 7. Any number below 7 belongs to the acids. When air pollution mixes with rain, it creates water that drops below a pH of 5.6. This acidic rain washes over forests and rivers, stripping nutrients from the soil and leaving behind dead trees and damaged ecosystems. This damage happens on a much smaller scale inside your mouth, too. When bacteria feed on the leftover sugar on your teeth, they produce acid. If the local pH drops below 5.5, that acid begins to eat away at your hard enamel. Animals also use this acidic power for defense. When a honeybee stings you, it injects a tiny amount of concentrated acid under your skin, resulting in an immediate, sharp pain. To treat that sting, we turn to the upper half of our scale, from 8 to 14. This is the basic or alkaline zone. If you dab a mild household base like baking soda onto a sting, it helps counter the acid's bite. By reading this numbered scale, we can measure the strength of the liquids around us and choose the exact right chemical to stop them from causing harm. Acids are highly aggressive when they encounter certain materials. If you drop a piece of zinc metal into an acidic liquid, the acid breaks the metal apart. It forces hydrogen atoms out, which bubble up and release a gas with a distinct popping sound. You get a similarly vigorous reaction if you pour an acid over materials that contain carbonates, like crushed eggshells or limestone. The acid attacks the solid structure, creating a fizz of carbon dioxide. So what happens if these aggressive acidic liquids run directly into a strong base? When the two teams collide, they participate in a process called neutralization. The positive hydrogen from the acid and the negative hydroxide from the base meet, lock together, and fuse. They form H2O, pure water. Two highly reactive, potentially dangerous liquids meet, and instead of destroying the environment around them, they perfectly cancel each other out, leaving behind something completely safe. But water is not the only thing left behind in this collision. Every time an acid and a base neutralize each other, the leftover chemical parts combine to form a solid byproduct that we call a salt. The most recognizable version of this byproduct is sodium chloride, the common table salt we put on our food. We mine massive blocks of it from deep underground, digging into the floors of ancient, dried-up seabeds. Because our bodies need this specific salt to survive, the right to harvest it has driven historical conflicts. In 1930, Mahatma Gandhi led a 240-mile march to the sea, specifically to protest salt taxes, turning this simple mineral into a central symbol in the struggle for human freedom. We use this harvested salt for its ability to be broken apart. By dissolving it in water and running a strong electrical current through it, we generate separate chemicals that act as specialized tools. This process yields chlorine for disinfectants, sodium hydroxide for soaps, and the raw materials for baking soda and washing soda. By splitting salt, we generate the chlorine needed for bleaching wood pulp in paper factories, and the sodium hydroxide used to create artificial fibers for textiles. This single chemical reaction provides the raw building blocks for modern hygiene and manufacturing. Some of these salt crystals look and feel dry, while actually trapping water molecules inside their rigid geometric shapes. When we apply intense heat to a blue copper sulfate crystal, it turns white as it loses this water, releasing visible steam in the process. We use this property in medicine with a white powder called plaster of Paris. When a doctor mixes water back into this dry powder, the plaster absorbs the moisture, linking the molecules back together. The sludge rapidly cures into a hard, protective cast to hold a broken bone perfectly still. From the sharp pain of a bee sting to the fizz of a stomach remedy, these interactions all trace back to that invisible tug-of-war between positive hydrogen and negative hydroxide. Every time we bake a cake, wash our clothes, or treat an injury, we are applying the rules of chemistry to restore balance to our physical world.